In this video, we're going to talk a little bit more about block time analysis. In our last video, we talked about the simplest case of a sequential program, and this time we're going to increase the complexity of the program a little bit and find out how we can deal with that. The application we're going to use is the same one we used the last time, this block time application. And as a review, this is the kernel of it. It's basically the find stir application. That is, it searches a set of directories, gets all the files that match a particular pattern, reads all the lines of all those files, and then if there's a match to another regular expression, then it will add that file to a results list. So it does. The important aspect of this application is simply that it needs to have both block time, that is disk I/O, and CPU time. The thing that's different about this time is that this particular application has the ability to either do all of that work on one thread or do it concurrently by calling this function called do work. And do work is just this thing that takes a list of work and an operation, and it keeps pulling a thing out of the work list and doing the operation, pulling a work out of the work list and doing an operation, and it does that on several tasks. And in fact, it does it on processor count times 2. So this happened to be done on a dual processor machine, so it will do 4 concurrent threads, and it will basically walk all of those directories and files concurrently using 4 threads. And so how would we analyze such a program? And of course, you start up Perfview. And as mentioned before in the first video, one of the important things you have to do is you have to click this thread time box. This is also called thread blocking on older versions of Perfview. And that will turn on what's called context switch events. And these are the events that tell you when a thread gets the processor and relinquishes the processor. And using those events, you can form a view of real time, of wall clock time of the application. So once you've clicked thread time, you can hit start collection, and everything works as it has done previously in the previous video. I have already done that, so I'm not going to do it this time, and the result this time is this block time parallel. And again, I'm going to start with looking at, and because I've done the thread time checkbox, I get these 3 new views when I'm opening the data. And this one, again, this thread time stacks is the one that we saw last time, and that's where we're going to start again. And we're going to look at my block time application, but this time it's in parallel, and waiting for symbol resolution. And I'm going to go to the call tree view, and you can see that unlike the previous one, we have quite a bit more threads happening before this time around than before. And you can also see that the main thread, here's the startup thread, uses relatively little CPU, 98 milliseconds of CPU, but that a little bit into the application, a bunch of new threads get started, and that's these threads. You can see that they're thread pool threads, and in fact, 4 of them, not surprising because we know that 4 of them were the application spawned off 4 threads, have a fairly high amount of CPU. And then everything else you can see uses almost no CPU. So you can already sort of see the broad outlines of this particular application with a main thread. And in fact, let's go ahead and search for main. And here it is. Here's the main program. And we can find out what was it doing. And so we can see that it went into scan directory and then do work. But then inside do work, all the main thread does is block on wait all. So it spends a lot of its time, in fact, 8 seconds of its time, just blocked waiting for all the other threads to finish. And really the interesting work is happening over in these threads. Now, and again, we can look at one of these threads and we can open it up, and we can see again, these wacky names which represent anonymous delegates, and I can do a right-click, go to source, and I can find out what those were. And in this case, you can see that there is a anonymous delegate that goes to right there that is doing this kernel, as I mentioned the first time, that the actual heart of the application is being done right here. But now it's being done by 4 threads simultaneously. I should mention that the full text of this application, as well as these data files that I've collected, are available as a companion download associated with this video. So you can go and look at it yourself and experiment with it and ask questions to me and so forth. And you can see actually the breakdown is very, very similar to what it was the first time around, which is not surprising at all. The breakdown of block time is right here, and you can sort of see that of the 10% this particular thread did, 8% was in this anonymous delegate, which called read lines and then get directories and so forth. This is going to look very much like that synchronous case, and so I don't really want to talk about that too much. But what I do want to talk about is that you can see that this application, even though it's not that much more complicated than the previous one, it's going to get harder to find the thread of interest. Like the technique that we used last time to find the thread of interest was look for a function that we know is interesting, main, and then look what its extent was, and zoom in on that thread and that time. Well, that won't work now because the main thread is just sitting here waiting. Well, it'll tell us that the main thread is waiting, but that's not really that interesting. So we want to find a way of finding all of these other pieces that we can sort of identify here just by coarse analysis, but in real analysis you usually don't have that much information, and you really don't know. It would be much more difficult to determine that these thread pool threads were doing something useful and this one wasn't, and so we need a way of dealing with that problem. And the way we're going to do that is this other view called the thread time view with tasks. And I'm going to just open that up for a second. And again, I'm going to go to block time. And I'm going to talk a little bit about what this view does. It looks a lot like the previous view. In fact, if you opened it up and we went to the call tree view, it's going to look surprisingly similar in that there's still all of those threads. It's just a different view of the same data. So it really should add up to exactly the same amount of time at the top and so forth. But it's a little bit different. And in order to explain that difference, I need to go back to the source a little bit. While this is the kernel of each thread's work, I want to talk a little bit about how the threads got their work, and that's what this code here. That's what this function do work does, and this is the body of that. And in fact, frankly, the most important aspect of this body is right here, where it grabs a piece of work, it tries to get a piece of work, and then does the operation on the work. But the thing that's most relevant for us at the moment is that I use tasks to create this work. And tasks are nice because the .NET runtime can do more for us because we have used tasks. It provides a bunch of value that we wouldn't have otherwise got. And one of the pieces of value is that a task knows who started it. So there's always a start new somewhere. And therefore there's always a thread that wanted that work to proceed. And then there's the actual work. And so the .NET runtime can emit events every time a new task is created and every time the task starts. And so the way that the tasks are typically used is you just have lots of little small items that you needed to have done, and you just tell some other task to go do them. Well, what that means is that we can hook those things up. We can hook up the fact that because the main thread started these new tasks, it's sort of responsible for them. That is, it gets charged. It's sort of like parents getting charged for their kids' credit cards, So in the same way, we can now do a roll-up in which anything that a subtask does gets charged to its parent. And that's exactly what this thread time with tasks view does. So you'll notice in this view that there are still these thread pool events or thread pool threads, and they still take the amount of CPU time that they did before, but they do it in but notice that the inclusive cost in this view is 0 or almost 0. Actually, there's a very small amount. These small amounts are the amount of time that these threads spend that isn't in a task. And you can see that they happen sort of only at the beginning and only at the very end. All the cost associated with these threads has now been removed from the thread, because they shouldn't be charged for this, but instead they're charged to the guy who caused them to be. And where is that? That's the startup thread. So remember, before, the startup thread, it only has 98 milliseconds of CPU time, but notice it's now being charged with 40,000. That is, all of the time that was associated with these guys is now been put up here. And in fact, it's even better than that. So let's go ahead and open this up. So we can see that there's the main program. It calls do work just like it did before. And we still have, let's see if let me put a 0.1 folding, which will clean up a lot of this. You can still see that there's this wait all, just like we had before. But what's also true is that you can see that start new, and in fact, block time did call start new before. It just was it was just so small that we didn't really care about it. But because this guy called start new, now this new pseudo node has been put in called task scheduled, and you'll see that what this means is that start new caused 4 tasks to be scheduled, one on each of these threads, which are these threads down here, and then their costs are just put in at this point. So all of that work is now being charged to the task that created it, and this works a lot of the time. And in particular, so you can see that this could be handy, because now the program looks a lot more like a sequential program. That is, main caused work to happen, and just like in the sequential case, all that work happened on this thread. Well, even though it doesn't happen on this thread anymore, it all gets charged to this thread. Now, it's not perfect, though. It's important to realize that in the sequential case, there was still only one thread, so you never had a problem with double counting. Here, I do have a problem with double counting, because I actually seem to have 40 seconds of time, wall clock time, when in fact the end-to-end time was only 8 seconds, right? So we're getting double counting on time because not only do I have all these tasks, but I also have the task wait. So here's the main thread waiting, and here is all the work that the other threads are doing. That is the wall clock time that those other threads consumed is also on here. So this doesn't solve the double counting problem, but it does solve the attributization problem. That is, I can find interesting wall clock time or CPU time. So in fact, one of the more useful things you can do with this view is that you can sit there and go to the by name view, and you can say, I only care about CPU time, so I do include item on CPU time, and now I can go back to the call tree view and notice I get all my CPU time added up, but notice that the other threads, I didn't do anything to get rid of these threads. The only reason why they're not showing up is because I turned on folding, and so things that don't use a whole lot of time don't even show up. So in fact, now what it's showing me is that there is no significant amount of CPU time being used anywhere except as a result of the main thread. And so now I get to do what looks like a normal sequential analysis of this parallelized program. And it all worked because of this new kinds of attributization in which the costs of things that I am responsible for gets charged to whoever's responsible for them at the point where they're responsible for them. And so again, you get these beautiful view that looks a lot like a sequential view. And we're going to see this technique used again and again, this idea of finding ways of sort of rolling up costs in semantically relevant ways rather than the physical way that is done just because we can, if we roll up just by tasks, by threads and processes, which is the default. Okay, and that's pretty much what I wanted to show you this time around. In the next video, we're going to show you about what to do in an ASP.NET application and the cool additional support Purview has for that.